Well, let's continue to discuss the output characteristic of the MOSFET. Reviewing the two animations of the operation of the MOSFET and the transfer characteristic of the MOSFET in previous part, we can get the operation conditions of the MOSFET in these two regions. When UDS is larger than 0 and less than UGS minus UT, the MOSFET is turned on and acts as a resistor, seen from its drain and source terminals. It means the MOSFET is operating in the resistive region when UDS is larger than 0 and larger than UGS minus UT. The MOSFET is operating in the saturation region and acts as a current source, seen from its drain and source terminals. Certainly, the equivalent resistance and the current source value are controlled by UGS. When it's operating in the saturation region, the equivalent current source IDS is a quadratic function in terms of UGS. As we've discussed in Lecture 9, it's a nonlinear controlled source instead of a linear controlled source. K is a constant determined by the element's characteristic and the structure. Now we summarize the conditions and the properties of the MOSFETs operating in different regions. The first is the cutoff region. When UGS is less than UT, the MOSFET is turned off, which means no current flows from the drain to the source. The property is IDS equals 0. This is a corresponding circuit model. It's an open circuit between the drain and the source. The second is the saturation region. As we discussed just now, the operation condition is that UDS is not only larger than 0, but also larger than UGS minus UT. It's equivalent to a current source between the drain and the source terminals. The current source value is a quadratic function in terms of UGS, which means it's a nonlinear controlled current source. This is a corresponding current model, circuit model. A voltage-controlled current source is applied. The third is the resistive region. When UDS is larger than 0 and less than UGS minus UT, it's equivalent to a resistor between the drain and the source terminals. This is a corresponding circuit model. It's represented by R-on. R-on is a voltage-controlled resistor whose resistance is controlled by UGS. According to the two possible operation states when the MOSFET is turned on, we can build the corresponding circuit models. The first is SCS circuit model, which means switch current source. It's a switch current source circuit model. When the MOSFET is turned off, it's a turn-off switch. When the MOSFET is turned on, it's equivalent to a current source between the drain and the source terminals, which is a nonlinear voltage-controlled current source controlled by UGS. You should pay attention to the operating conditions of the two regions. As we talked about before, the MOSFET applied in the amplifier of the headset is operating in a current source when it's turned on. The MOSFET is usually used to manufacture the small signal amplifier based on this property. The second is SR model, short for switch resistance. Its switch resistance model circuit is like this. When the MOSFET is turned off, it's a turn-off switch. When the MOSFET is turned on, it's equivalent to a resistor seen from its drain and source terminals, whose resistance is similarly controlled by UGS. You should pay attention to the operating conditions of these two regions. When UGS is less than UT, it's turned off. When UDS is larger than 0 but less than UGS minus UT, it's operating in the resistive region. Based on this property, the MOSFET is often used in the digital circuits. In the coming lecture, we will learn how to constitute various logic gates with MOSFETs. In these logic gates, the MOSFET is operating as a resistor when it is turned on. In fact, we can see from this model, when the MOSFET is turned on and operating in the resistive region, it's an electronic switch, which is not so ideal. Why is it said to be non-ideal? For an ideal switch, we hope that its resistance is very large when it is turned off, while the resistance best to be zero when it is turned on. In this circuit model, IDS is zero when the MOSFET is turned off, which means it's an open circuit between the drain and source terminals, and the resistance is infinite. However, when the MOSFET is turned on, the equivalent resistances are on instead of zero. This is really a disadvantage of the MOSFET applied in the digital circuits. We will introduce some methods to eliminate the influence of R-on later.